Hello, class. Okay, so today we're going to talk about something called the Second Law of Thermodynamics. And there's a lot of different ways of stating the Second Law of Thermodynamics that are all equivalent to each other. So you can state it one way and then show that the other ways that you could state it follow from that. So if you look online, Second Law of Thermodynamics, you might read different things, but they are all equivalent to each other. So what we're going to adopt as our second law, what we'll take as our statement of the second law. Say we have two objects, one hot and one cold. And what we're going to state is that our definition of the second law is that heat will flow spontaneously from an object at a higher temperature to an object at a lower temperature and will not flow spontaneously in the reverse direction. So if you let's look at two objects. Let me erase this arrow. Let's say we have an object at 300 Kelvin and an object at 200 Kelvin. And say we just bring them together, if heat just spontaneously went from this object at 200 Kelvin to the object at 300 Kelvin, that would be a violation of the second law of thermodynamics. Now, we can make heat flow in this direction by using something like a refrigerator or heat pump. We can reverse the normal direction, but that requires work from the outside. So if it does so spontaneously, that would be a violation of the second law of thermodynamics. Now, this it's called a law of thermodynamics. And there's something different about this than, say, Newton's laws of motion. And Newton's laws of motion are just like statements like, this is how the universe works. These are the fundamental rules that govern our universe. We now know that Newton's laws aren't really fundamental. They're only valid under certain circumstances. The kind of circumstances we're most familiar with, but they did have to be replaced as we learn more. Like in the 20th century, we had the theory of relativity and quantum mechanics. But it's still a statement about how the universe works. It's just not a 100% accurate statement. The second law of thermodynamics is something very different because it's not even really saying that something like this cannot happen. What the second law of thermodynamics is saying is that something like this happening is extremely unlikely. It's really based on probability. So if we place these two objects together and heat did flow from the colder object to the hotter object, that would not violate any actual laws of physics. The second law, but this in theory could happen. We never observe it happening because it would just be an incredibly rare event. So just as kind of an example of something that would not violate any laws of physics, other than these that are based on probability, let's say I took this glass of water and pushed it over the edge. So it falls and it shatters. Now, of course, no one would be surprised by that event. It falls, it breaks into a bunch of pieces. Sure, we've all seen things like that happen. But what if you came into a room and you saw the result of that? There's a shattered glass on the floor. And what if all those pieces kind of gathered together and jumped up onto this shelf and in this form of a glass? So it looked just like this. So basically, if you watch this process happen in reverse, is that something that's theoretically possible? Or would that violate any laws of physics? Now, you might think one thing it would violate for sure is gravity. How could these pieces jump up onto the table? It turns out it would not violate that. any laws of physics other than these kind of statistical laws. So again, if you think about like how could these pieces of glass jump up onto the table? Well, just think of the reverse process. When we push this object, it has kinetic energy, and then when it hits the ground, it shatters, it stops moving. So all that kinetic energy was dissipated. It goes into the ground. And so the molecules that make up the floor are going to absorb that energy and they'll just oscillate more rapidly. And so it is possible that the molecules on the floor could hit a glass, like a shard of glass, hard enough to fling it up onto the table. If you just look at this process of what happened, if you just play that in reverse, these kind of things are possible. Except we never ever observe them. Like the probability of, say I did push this over and it shattered. So I'm stating that it's possible that just through purely random chance, like the molecules on the floor are oscillating kind of randomly. And what's the probability that they would all happen to be moving just right so that they all like move upwards and hit a piece of glass and fling it with enough force to fling it back up onto the table? What are the odds of that happening? It's something that would simply never occur in practice. Just because, if this room existed since the Big Bang, we would never expect an event like that to occur. The probability is so low that even in the entire life of the universe, something like that just could never happen. So, the second law of thermodynamics is, in a sense, just as accurate, or just as reliable as the fundamental laws of physics, but there's that fundamental difference that it is based on statistics and not some rule of the universe. It's just based purely on statistics. Okay, so that's, again, just the idea of heat flowing spontaneously from a hot object to a cold object. Again, it's purely a statistical result. That's just the more likely way things are going to go. When I say more likely, it's so likely that you'll never ever see the reverse happen. Okay. Now, I want to talk about something else. Something called a reversible process. And a reversible process is when we have a system and its environment, which is everything outside. So here's our system, and outside of that we have our environment. And a reversible process is when the system and its environment can both be brought back to the initial conditions. So say our system is in a certain state and the environment is in a certain state. So if the system changes, say it goes from state A to B. An example of that, say our system is a gas in a cylinder. And let's say in the real world, say you actually have a cylinder, like in your car, and you push this piston down. You compress the gas. Now, can you reverse it back to this initial state where the piston was up here? Well, of course. You can just lift the thing back up. However, that would be an irreversible process. You've returned this system back to its initial state. However, the environment would be different. The environment is everything outside the system. So in the real world, if you push this piston down, you've got the piston and the walls of the cylinder are in contact, and there's going to be some friction. So some energy is going to go into the environment in the form of heat. And if you lift the piston back up, again, we have friction to deal with, so we're not going to have that. Friction is an example of an irreversible process So like when the piston goes down, energy is going to go from the system to the environment. And then if you force the thing back up, if you force that piston back up, you're not going to reclaim that energy just because you're going in the opposite direction. Friction doesn't care what direction you're moving. So in the real world, something like this would be an irreversible process because there's friction involved. Now, you can make it approximately a reversible process by minimizing friction. Like in a car, they do a pretty good job of that. You have this coating of oil, and there's always some friction to deal with. So a reversible process is when the system and its environment can be returned to its initial state. And again, that's going to tie into the second law of thermodynamics. Now again, it is because it's based on statistics as well. If we lift this, say we compress this gas, if we lift the cylinder, is it possible that energy that dissipated due to friction, it turns into heat? Is it possible that that's going to come back into its original state? Yeah, it's possible, but again, extremely unlikely. And the numbers we're dealing with, when we say extremely unlikely, it basically means never going to happen, even in the lifetime of the universe. Okay, so what I want to do is let's look at write it over here. Our basic stuff about engines. So just based on First Law of Thermodynamics or conservation of energy, say we have a hot reservoir and here we've got our engine. And a cold reservoir. So again, the way that engine works, we take heat from the hot reservoir, get out work, and we have to dump some energy into that cold reservoir. So again, heat's normally flow from hot to cold, and what the engine does, it kind of takes some of that flow of energy and turns it into useful work. And our goal is to get as much work as possible out of this. So again, let's talk about the efficiency of an engine. First, let's look at the first law of thermodynamics. What goes into the engine is equal to what comes out. And again, we have the efficiency of an engine, that's what we get out of it, which is work, divided by what we put into it. So we have W over QH. Okay, so again, that's all review. Just put that off to the side. So what I want to do is, say we have a hot reservoir. Which is at a temperature TH, and a cold reservoir. At a temperature TC. And here we have this engine. I'm just going to call it engine X. Okay, so we're getting work out of it. So again, literally I just wrote down exactly what we have over here. However, what we're going to do is we're going to take this engine. So again, we have some engine that's, heat engine. And it's taking advantage of the difference in temperature here to do some useful work. And what we're going to do is we're going to use this work to drive a Carnot engine in reverse. So remember, for a refrigerator or a heat pump, fundamentally doesn't matter how we do this. We're basing this on things like conservation of energy. So what we're going to do is we're going to take this work to take energy out of this cold reservoir and dump it into the hot reservoir. So we're going to call this Q, because now we have two different things. We're taking QH from the hot reservoir, and the Carnot engine is putting some heat back into the hot reservoir. So just to distinguish them, we'll use QH, QH prime, QC, QC prime. Okay. So we've got some engine here that's driving a Carnot engine. So I'm also going to write here for a Carnot engine. What we did last time. There's different ways we can do this algebraically. Okay. So, this is what we're going to do. Now, I'm going to make an assumption. Let's say that this engine X is more efficient than the Carnot engine. So the Carnot engine, we know how to calculate its efficiency. Or we can write the efficiency of an engine basically just by using the first law. So W is QH minus QC. And then the first term we have a QH over a QH, that's 1. So yeah, the efficiency of any engine is 1 minus QC over QH. And for a Carnot engine, QC over QH would be TC over TH. So again, we have these two reservoirs. We know what the efficiency of a Carnot engine is. So let's say we build an engine that is more efficient than a Carnot engine. And let's just see what would happen. So we're going to use this engine to drive this Carnot engine in reverse. So let's look at, here, let's just go with this. So the efficiency of engine X, that would be W over QH. And we're saying that that is greater than the efficiency of the Carnot engine, which is W over QH prime. And so, basically what that means is QH prime is less than QH. So, like, say W is 1,000 joules. Divided by, say, just to make things easier, okay, so yeah, just W is going to be the same on both sides, so let's just pick a number. So again, if this is true, if this inequality is true, it means QH prime, oh sorry, I think I wrote that, did I write that right? Let's check. Sorry, QH prime, yeah, I reversed the directions. Yeah, QH prime has to be greater than QH. So again, let's say QH was 10, QH prime would have to be bigger than that, just because we're dividing by it. So we have to divide by something bigger to make this number smaller overall. So, yeah, if you try, I know inequalities, you have to be a little careful working with them. Easy to mess those up. So, yeah, you can just try making up numbers. Like, imagine QH prime was less than that and see if this inequality would hold. No, it would not. So we have QH prime is greater than QH. Or QH prime minus QH is greater than 0. Okay, I'm going to write that down over here and then erase this part of the board. So we have this result here, QH prime minus QH is greater than 0. And that comes from this idea that our engine, X, is more efficient than a Carnot engine. So I'm going to clear up some space here, but this is the result, which we'll come back to. Now let's look at the first law of thermodynamics real quickly. If we look at the first engine, we have QH. What goes into the engine is equal to what comes out. So that is QC plus W. And over here, what's going in, well, let's say what's coming out. I think that'll be a little easier. That equals what's going in, which is QC prime and W. Now, W is common for those. I'm going to write this a little more clearly. So if we solve each of these equations for W, we can say, like here, W is QH minus QC. And looking at this equation, W is QH prime minus QC prime. And so what I'm going to do is just move terms around. Like here we have QH prime minus QH. So let's bring this term over here. So on one side, here we'll do it in a few steps. Let's bring this term over here and this term over here. So we're going to have, moving this over here, we're going to have QC prime minus QC. And on this side, say we move this over here, and then we're moving this over, so we have QH prime minus QH. Okay, so let me just double check the algebra really quickly. Yeah, that looks good. So this here, QH prime minus QH, that's what we have. So what I'm going to do is I'm going to define Q to be equal to QH prime minus QH. It's a pain writing all these absolute value signs, but they are important since we have this convention. And we know that that is equal to QC prime minus QC. So those are equal to each other, and so let's just call that Q. And so this here, then what we have is Q. I guess we don't need absolute value here because it's going to be greater than 0. Okay. So now I'm going to erase this part. And we're about to get to a very important result. Again, this is a very theoretical kind of topic, and it's kind of very kind of deep thinking that went into this. And so it's one thing to follow along, but right now you probably have no idea where we're going, but we're about to get to a very important result. So what I'm going to do, let's say we put a box around this. So we've got our engine X and our Carnot engine. Say we put them in a box. So we're outside, we can't see what's going on inside this box. So from our perspective, what we're looking at, we have a hot reservoir and a cold reservoir. And then we have this box. We don't know what's inside. We can't see what's inside. Okay, so let's look at the hot reservoir. We know QH prime minus QH is greater than 0, or Q is greater than 0. So QH prime is what's going into the hot reservoir. QH is coming out. So the net heat flowing into the hot reservoir is Q. And similarly, QC prime minus QC, same thing. QC prime minus QC is greater than 0. So we've got this net flow of heat out of this cold reservoir, which is also equal to Q. So basically what we've done by building this engine X, hooking it up with a Carnot engine and putting it in a box, is we've created a device that is taking heat out of a cold reservoir and just moving it directly into a hot reservoir without any external work being done. So again, we just have this box here. There's nothing, we're not putting any input of work into it. It's operating between, so if we look at the details inside, but outside, we've got a situation where we've got this flow of heat from a cold reservoir to a hot reservoir, which is only possible if you supply external work, which we are not doing here. And so basically, this box is impossible. We can never build something like this. This would violate the second law of thermodynamics. So remember, the key word in that second law says heat flows spontaneously. That spontaneous is a key word. Heat normally flows from hot to cold. We know we can make it reverse direction, but that requires an input of work. And this box is not taking any work from outside of the box. So we've apparently created an engine that can make heat flow from cold to hot just indefinitely without supplying any energy from outside. And the second law of thermodynamics simply does not allow that. So this is absolutely impossible. So what went wrong? You could kind of look over all the algebra, maybe we made a mistake somewhere. But no, what we've done in math, there's a term for this in math, where if you want to prove something is impossible, what you do is you assume that it's true, and show that that assumption leads to an impossible result. And that's what we've done. We started this whole thing on the assumption that this engine was more efficient than a Carnot engine, and that led to this impossible result that the second law of thermodynamics was being violated. And so the result is that this cannot be true. We've shown that our assumption must be false because it leads to an impossible result. So what we've shown in an indirect way is that the efficiency of any real engine has to be less than or equal to the efficiency of a Carnot engine. And that's why these Carnot engines are so important. They are the most efficient engines that could possibly exist. You'll never have a heat engine that can be more efficient than a Carnot engine. And that's really an amazing result because, remember, the stuff we're talking about, we say, okay, we have some engine. How does this engine work? Well, there's a lot of examples. But just based on these fundamental ideas of thermodynamics, like the first law and the second law, we can make this definite statement that there's a maximum efficiency possible between the, it only depends on the temperatures of these hot and cold reservoirs. So, another way of stating this, we know the efficiency of a Carnot engine. So if you have two reservoirs at temperatures TH and TC, this gives you the maximum possible efficiency that you could have for any real engine. This is an upper limit. Now I said less than or equal to. Typically it's going to be less than. The only time we'll get an equals is if we build a reversible engine, which means no friction involved. So realistically speaking, the efficiency is always going to be less than the efficiency of a Carnot engine. So again, this is a very profound statement because, like, let me just give you a numerical example. Let's say you have two hot reservoirs. So like 300 Kelvin is room temperature. So let's say there's something very cold. You know what, let me change that. Let's say 300 is a cold reservoir. So let's say you have something hot, 400 Kelvin. Say you dig deep into the ground where it gets very hot. You know, if you go down far enough, you get magma. So the temperature increases when you go down. So say you dig down, and again, we're talking about like geothermal energy. Let's say you can dig a tunnel down to where it's like 400 degrees Kelvin or 100 degrees Celsius. We're, ready to boil water here. And you could build an engine that's going to take advantage of this flow of heat that would naturally occur. And we can easily calculate the maximum possible efficiency. Let me just clear some room here. So a Carnot engine operating between these two temperatures would be 1 minus 300 over 400. They're both in Kelvin, that cancels out. That would be 25% efficiency. Yeah, 3 over 4 is 0.75. So the efficiency of a Carnot engine operating between these temperatures is 0.25. So if you want to build like a geothermal engine that would take advantage of that source of heat that's underground, the maximum possible efficiency you could hope for is 25%. You can never do better than that, no matter how much you pay your engineers. This is just the fundamental limit. To go beyond this would violate the second law of thermodynamics. And so that's why we talk so much about Carnot engines. Because it's a theoretical engine, except it is the most possible engine that you could ever have. And I think that was kind of the goal that, that's why Carnot came up with this. I'm pretty sure that's what happened. Where he wanted to think, like, what's the maximum efficiency you could possibly have? And so he came up with this idea of the isotherms and adiabatic curves to define the cycle. And, and again, it's also nice that it's a very easy thing to calculate. So a real engine would have a less efficient, lower efficiency than that. Now, I can try to find, there's a really interesting kind of engine you could design. I have real trouble trying to draw this, but there's a good description on YouTube. I can actually post a link of this YouTube video. They talk about this really amazing kind of engine. The idea, I'll just real briefly talk about that. Again, the hard part for me is drawing it. But say you've got a wheel with kind of like teeth almost. And let's say a situation like this, where if you turn the wheel this way, you're fine. It can like slide this. See, there's like a spring kind of pushing this inward a little bit. Except you can turn this wheel and it can, there's like a ramp here, so it can, lift this up and then it'll drop back down. But if you try to turn it this way, like this is a flat edge, it's going to hit this obstruction and it's not going to go. So say we have a chamber with a gas, and we have basically the result of this contraption is we have a wheel that can spin only in one direction. You cannot really get it to spin the other direction. So you might think here is a way we can violate some laws of physics here. Because these molecules are moving around and hitting this object, and maybe they'll hit it just right to cause it to rotate counterclockwise. Now, normally, let's back up for a minute. Say we have a wheel with some, like, paddles, for instance. And it's surrounded by a gas, and so these molecules of gas are colliding with this, and they can cause it to rotate randomly. Again, this would have to be a small enough wheel, because if it's a large object, the forces involved would be so small that it would never do anything. It's not going to rotate on its own. But if you made a really small wheel, it's possible that, like just say like on this wheel, slightly more molecules hit upwards than downwards. And so it's going to rotate counterclockwise. And so you might think, well, here you can make an engine out of this. You can have this thing that's just going to rotate randomly. Problem is, it's going to go back and forth. You're not going to get anything useful out of this. However, you think if you design something like this, where you only allow it to rotate in one direction, that maybe you could build an engine. You're not going to get much out of it, but maybe you have this gas and it's just going to spin in one direction. But it turns out that this obeys the laws of thermodynamics, just like any other engine. And again, I did see, I'm going to have to find this, but I saw a really interesting discussion of this on YouTube, so I think I'll just post that link. It's kind of crazy, but they can show that this actually obeys like what we were talking about. So this really unusual idea for how to make an engine, but that obeys the laws of thermodynamics as well. So I'll definitely post that link. But yeah, basically, I think that'll be it for this lecture. Now, for this section and the first 4 chapters in the book that we're covering in thermodynamics, there's one more thing we're going to talk about. And, next we're going to go, and it's going to tie into, this Carnot engine and efficiency, things we've been talking about. So the next lecture is going to be on entropy, something you may have heard about before. We're going to talk a little bit about that. And also, there's the third law of thermodynamics, which, just put at the end. We already actually talked about that, but we'll kind of review that again at the very end. So basically, one more lecture on this subject of thermodynamics, and then we're done with this section. But that'll be it for this video.